Now let's move on to section 2 of this notebook, Exponential Models 1. As a matter of fact, even though I named it as Exponential Models 1, don't be intimidated. We're just talking about some basic applications of exponential functions, which are kind of scattered around in our textbook, partly in 4.1, partly in 4.2, partly in 4.7, I think, kind of all over. But I wanted a little bit more systematic approach, so I did a little bit of classification and presenting all those in a single section here. I'm going to emphasize 3 types of models here. Number 1, compound interest model. Number 2, logistic model. And number 3, radioactive decay model. The easiest of the bunch is the compound interest model because this is straight ahead exponential function. We have base A and then t power basically. So this is going to be an exponential function just growing up. Now what are these characters? B of t means the balance of your investment CD account. P0 is the principal that you invested initially, and R is annual interest rate, and N is a number of compounding reinvestment each year. For example, if you purchase an investment CD account, then depending upon your contract, the money can be reinvested either once a year, twice a year, 4 times a year, quarterly, that's the most common, or 12 times a year, monthly. I've seen that one too. And those are, those are the N values. So common N values are kind of like this. Annual, personally, I haven't seen this kind of investment CD account. Semi-annual, well, I've heard about it, but not much. Quarterly, I have owned many of them. And I own one too, even as of now. And monthly, I owned one too when I was in Illinois. But N equals 4. Quarterly reinvestment, that's the most common case. And how does that work? Well, that works according to this formula here. Put those N value downstairs here and get R over N so that you get not annual interest, but you can get monthly interest or quarterly interest, things like those. And then the power will be not just T for T years, but NT. Basically, it's number of quarters or number of months, kind of like those, number of compounding periods. How does this formula work? Kind of goes like this. Initial balance will be the principal, the money you put in. Now, 1 over N, that looks a little bit intimidating, but actually 1 compounding period later, so 1 month later, for example, when N equals to 12, then 1/12 of a year later, or 1 quarter later when N is 4, then we have the principal, and then this is the amount of money that grew through the reinvestment. And we have the interest rate, annual interest rate divided by that N, so that we have quarterly interest rate or monthly interest rate, and that part is interest. Now, if you do not take the interest and then just keep it reinvested and compounded, then you can factor P0 out, and this is going to be your new balance after the first quarter. Now, after the next quarter or next month, after the second compounding period, this highlighted amount is the money that is carried over from the previous period, which is over here. And we have to multiply that amount by the interest rate, R over N, the monthly interest rate, R over 12, or quarterly interest rate, R over 4, things like that. So the highlight part is the interest. Now let's apply some algebra, do some factorization. Then what do we get? P0, 1 plus R over N, that highlighted part is a common factor. I take it out, and I have 1 plus R over N again. So put those together, and we have second power. By now, I think everybody saw the pattern, but let's just do it once more. Third quarter later, That's where we start because that's carried over from the previous period. And that times R over N is the interest. That's the amount grew. Okay, let's apply some algebraic manipulation again. Factor out P naught 1 plus R over N squared and do further manipulation. We have the third power. And okay, pattern is really clear. Just keep it doing it over and over again. And in general, we're going to get this formula, which is something we wanted from the first place. So what did he do? As a matter of fact, we proved this formula. Now, shall we do a problem here? Okay, let's go ahead and do that. The amount of money resulting from investing principal P for time t years, an annual interest rate, compounded n times a year, can be expressed as follows. Okay, there. Calculate the money present if $1,000 is invested at 5% interest for 7 years compounded, yearly, quarterly, monthly, and daily. So n value is 12 for 12, and 365. And, well, here it is. I just use Mathematica to do the computation. 1000 P naught, that's P principal, 1 plus R over N, parenthesis, and N times T power O is difficult to highlight, okay? And calculate it for n equals to 1, n equals to 4, n equals to 12, n equals to 365 for 7 years. And I've just ran Mathematica program and I have these figures. As you can see, the more compounding you do, the more money you're going to get in the end. But it's not going to grow indefinitely. As you can see, the difference between just reinvesting once a year versus quarter, 4 times a year, well, there's a significant difference. But compared with 4 times a year versus 12 times a year, not much difference. 12 times a year and 365 times per year, not much difference. If you change this into something like, let's see, how about every second? 365, 24 hours per day, and then 3,600 seconds per hour, and just compounded every second. Again, the difference isn't much, as you can see. And this kind of converging behavior is related to, as a matter of fact, natural exponent E. Okay, let's move on to the next model, logistic model. This one is related to population model. If you just put a pair of rabbits, for example, and let them grow, then if there is infinite amount of resources out there, infinite amount of space, and no predator, no nothing, in that case, just like compound interest model, the population of rabbits will just go on forever. But in reality, there are limited spaces, limited resources, there are competitions and there are predators and so on. So we can expect some equilibrium. And equilibrium, E, is mature population. Oops. Come on, that's a numerator. And A and K values depending upon circumstance, depending upon what kind of species we are dealing with, what kind of environment we are dealing with, things like those. Why do we have equilibrium? Here's the proof, as a matter of fact. Replace T by infinity, then what do we get? K is going to be positive real numbers, so e to the, let me increase the font. Okay, e to the negative k times t, but t is replaced by infinity, so what do you get? E to the negative infinity. What is e to the negative infinity? Do you remember the graph of the natural exponential function? Let me show you that graph. There's got to be a graph of natural exponential function. Well, here it is. And as you move to the left hand side, you have horizontal asymptote 0. That's clear. E to the negative infinity is going to 0. So what do we get? This part, or a times that, is 0, and consequently we have E. So as we take really infinite amount of time, we have mature population, stabilizing population E. What if go to negative infinity? In that case, negative infinity will replace this t over here. So we have e to the positive infinity downstairs, which is infinity. So we have e over infinity basically, and that's going to be 0. So we're going to have 2 horizontal asymptotes. And let me show you a picture. Here is a graph of a logistic model, I think. Yes. Well, this one is related to a herd of deer introduced onto an island, and then mature population was 2,000. In that case, as you can see, we have horizontal asymptote that's 2,000. So that's the equilibrium. And then in this problem, well, we are beginning with 500 individuals, 500 years, and then find out or estimate the population 1 year later, 20 years later, and 50 years later. And it's just this model and a plug in t-value 1, 20, and 50 respectively. And you can use handheld calculator, but I just use computer algebra system and got these figures. 515.149. We're talking about integer number of deers, so approximately 515 deers, and 851.79, that means 852 deers, and so on. So logistic model with the kind of graph, we have 0, y equal to 0, and y equal to e as horizontal asymptotes. We have another problem, but I'm going to leave that to you. Now, let's move on to the third exponential model, and this time radioactive decay model. Kind of goes like this. Initial quantity Q0 times e to the negative kt power, and k is related to what kind of substance it is. Or equivalently, with some manipulation, it can be written like this. Q0, which is the initial quantity, and 1/2 to the t over capital T power, where capital T is called half-life. Let's see, let's open up a problem. Is this the one? Yes. Americium-241 is a radioactive substance used in common household smoke detectors. And this is common because it's relatively cheap and it's reliable, and most of all, it's relatively harmless. So it is used in common household smoke detectors. And radioactive decay of Americium-241 can be modeled as follows, and then 432.2, that's the half-life. So 432.2 years later, quantity will become the half of the beginning, half of the original, and then twice that later, 864.4 years later, 1/2 again, so we're going to get 1/4 of the original. But in this model, we just plug in t equals to 20, 200, 432.2, and so on, and run the program, and this is what you get. 10 years later, 20 years later, we have 9.68434 milligrams left out of 10, and an f of 200. 200 years later, we have 7.25602 milligrams left. And then 432.2 years later, that's going to be half of the original, so 5 milligrams. And then another half-life later is going to be a quarter, so 2.5 milligrams. Those two, C and D, can be done without calculator. But if you use calculator, you can answer all those questions. In any case, all these problems are actually easy as problem solving, because all you have to do is plug in those numbers and run your calculator. When the explicit models are given, there are 3 types of models, and all you have to do is work out with your calculator. And one more emphasis, please make sure you use parentheses correctly. Whenever I wrote this kind of problem in exams, that's where students make mistakes. Usually they don't, but if they do, it's where parenthesis is, and somehow they mess up computation and then they get wrong answer. Careful about that.